Hello, everyone. Welcome to today's webinar. We'll get started in just a moment here. All right, hello and welcome to the next webinar in our Earthquake Spectra Showcase series. Thank you for joining us today. Before we get started, I just want to take a brief moment to introduce EERI. My name is Elizabeth Angel and I'm EERI's Communications and Program Manager. And if you're not already familiar with us, the Earthquake Engineering Research Institute is the leading nonprofit organization bringing together people from a wide range of disciplines and fields who are working on the common mission of advancing earthquake resilience, both here in the US and around the globe. We have both researchers, practitioners, students, a wide range of folks, and we'd love to have you join us if you're not a member, so you can find out more at that link, which I'll also share in the chat. I also want to acknowledge that this webinar series is made possible by support from FEMA, from our Learning from Earthquakes Endowment Fund, and by EERI members like yourselves. And I want to thank our 2025 subscribing members, including our visionary subscribing member, Computers and Structures, Inc., as well as the others listed here on this screen and on this one in the bronze tier. So thank you to all of those organizations for supporting EERI and our mission. And if your organization is interested in becoming involved and would like to learn more about the benefits of subscribing membership, please check out our website or feel free to contact us. I also want to mention an upcoming webinar series that you won't want to miss. In April and May, we have a two-part webinar series that we're doing in partnership with USGS, which is going to focus on the 2023 US National Seismic Hazard Model. There's a recent special collection in Earthquake Spectra with a number of great open access articles about this model. And in the first of these sessions, we'll have a number of great presentations, sort of giving you an overview, talking about the science behind the hazard modeling. And then on the second one, on May 7th, we'll be talking about engineering applications, including kind of building code and other things. So you can see the full list of speakers and topics and register by finding that event on the list of our upcoming events, so that URL, but I'll also pop a link to it in the chat later in the webinar. And on that note, I'd like to turn it over to Kishor Jaiswal, a research structural engineer at USGS, who's also an associate editor, Earthquake Spectra, and he will be moderating today. Kishor?
Thank you so much, Elizabeth. Welcome, everyone. Welcome to the February 2025 Earthquake Spectra Showcase Seminar webinar series. My name is Kishor Jaiswal, and I'm a research structural engineer at USGS. At the outset, I want to thank Silvana and Elizabeth for facilitating this webinar on behalf of the editorial board. I want to welcome everyone and congratulate the two speakers today. If you're not familiar with Earthquake Spectra and EERI, I encourage you to go into the Earthquake Spectra website. Earthquake Spectra is a leading journal. It's a peer-reviewed journal of the Institute with a focus to improving the practice of earthquake hazards, mitigation, preparedness, and recovery worldwide. I think it's one of the top journals in the field, consistently rated with the highest impact factor. Each year, the Spectra basically issues 4 issues, each roughly about 30 papers. This particular issue of February 2025 had 31 research papers, 1 data paper, 1 engineering practice paper, and 1 opinion paper. So there is a wide variety of topics that are covered through this particular special issue. In particular, the February issue had number of papers on the 2023 magnitude 7.8 Turkey-Syria earthquake sequence, really some very important topic and discussing the impacts from that earthquake sequence. There were other papers covering broad range of topics from ground motions to basin response to earthquake risk and loss modeling and things like that. So it's very hard for the editorial board or even the editor-in-chief to just pick 2 papers for this webinar series. And I'm so happy that Professor Baker picked these 2 papers. And I want to congratulate both of these authors for being selected for this webinar series. We have 2 speakers today. Each of the speaker will be given about 20 minutes each. and then we will have a Q&A, which is for 15 minutes. So if you have questions, please hold those questions for us at the end. You can obviously use the window to type in your questions. If you have any questions you want to pose into the window. The first speaker we have today is Professor Lydell Wiebe. Professor Wiebe has received his bachelor's and PhD in civil engineering from University of Toronto. He's a leading faculty and is a full professor and acting chair of the Department of Civil Engineering at McMaster University. He has really led from his PhD days research wide covering the steel frame design constructions and really looking at various aspects of steel design and constructions. Today, he's going to talk about seismic loss comparison for buildings designed with ductile steel, seismic force resisting systems, and with controlled rocking brace frame. He co-authored this paper with, I believe it's student Amir Beni Hashmi. And so, Professor Lydell, take it away.
Thank you very much for that kind introduction. I'm assuming people can see my screen, but if not, someone jump in and let me know. Yeah, my name is Lydell Wiebe at McMaster University. For those of you wondering, we're about an hour from Toronto and an hour from Buffalo. And the work that I'll be presenting was done by Amir Beni Hashmi when he was doing his PhD. He's now a PhD graduate working in practice. And looking at comparing different seismic force resisting systems, both ductile, more traditional ductile systems, with some of these developing more resilient systems, and in this case, controlled rocking, through a lens of seismic loss comparison. So my plan for the 20 minutes or so that we have today is to dive into the question of, is it worth investing in a more resilient steel seismic force resisting system? And so the way that I'm planning to look at that is first to provide a little bit of context, looking at what we expect for seismic damage with modern steel frame buildings, and a bit of a crash course on controlled rocking braced frames. I imagine many of you will not be familiar with them yet. And then I'll go into some of the method that we looked at for this paper, the design archetypes we used, the modeling assumptions, and if we're looking at it from a lens of repair cost, how we did that. And then I'll dive into the results on structural performance, looking at the seismic losses, both from an intensity-based and a time-based perspective, and then overall this cost-effectiveness question before wrapping up with some implications and a bit of a shout-out to some related work. So starting off with some context related to what we expect with modern buildings, I'm sure many of you have seen some version of a discussion of what happened with the Christchurch series of earthquakes in 2010, 2011. The image that's on the screen here right now is the central business district, the downtown core of Christchurch, city of about 400,000 people, bounded by the 4 avenues shown in yellow there. And each of those dots is one of the buildings in the central business district. And the blue dots are ones where the decision was made after the damaging earthquakes to demolish. So about 2/3 of the buildings in the downtown core, even though not very many of them collapsed during the earthquake, the majority of buildings in the center of the city were demolished because of the earthquake there. And it's a reflection of this design that we have that is leading to damage. I also want to emphasize the idea that it's not just about the structural damage to it. So the first time I visited Christchurch was just over 2 years after the most damaging earthquake in the series, which was in February of 2011. And I saw the structure and I thought, I'm going to take a picture of this because it pictures for me this idea that they demolished 2 out of every 3 buildings. Here's this one. As far as I can tell, actually, from looking at it, I have no inside knowledge on this building. But from what I can tell, it looks like it's fine structurally. But the building on its left and the building on its right were both demolished. Why this one was not used, maybe something to do with non-structural, probably actually a lot to do with all of the other buildings in the area. But this was 2 years after the earthquake. This was 4.5 years after the earthquake in September. You see a lovely base isolated building going up in the background, and this one is still not in use. And last time I was in Christchurch was about 9 years after the most damaging series, and they finally have a for lease sign up in the front window there, but still not in use at that point. I'm guessing now it's finally occupied. But just to drive this point that it's not just about the structural damage, we need to be thinking about more than that. Even though if we are thinking about structural damage, there's been this push for many, many years to look at more resilient seismic force resisting systems. picked a few of the many references that I could here. Base isolation, which is not the focus here, but I do want to mention it's also a really important way of looking to enhance resilience. Goes back at least 40 years. If I'm talking about rocking, which is the focus for today, back in the 70s, there was work in New Zealand about applying it to a rail bridge. There was a bunch of tests that were done in Berkeley. The PRESS project was done in the 90s and kind of was a bit of a renaissance of these rocking systems. And so it's not particularly new, but it is something that it still hasn't quite gained full traction. And so we wanted to look at it here. To summarize how it works, and I'll look here at a controlled rocking steel braced frame because our focus in this paper was on steel systems. The idea of a rocking system is you're actually going to let the seismic force resisting system partially lift up from the foundation in response to rocking or to earthquake load. So if we look at a structure like this, and I plot the force displacement curve, initially, if you start loading it up, it'll deform like any other braced frame until you overcome the pre-compression of the brace. It doesn't know it's a rocking structure. But eventually you reach the rocking load, and at that point, when we reach zero force down there, now it's ready to start rocking. And so as you continue to push it, it will start lifting up from the base. That'll cause a softening response. And this positive stiffness would be contributed by post-tensioning. You don't always need post-tensioning, but it's commonly used in these controlled rocking systems. At least from a research perspective. The ones that have been built probably are more commonly without, but still plenty of examples with post-tensioning. If you unload it and go back in the other direction, you get this bilinear elastic response, which is characterized by this self-centering, where whenever the force is zero, the displacement is also zero. And then typically what you would do, this as it is doesn't dissipate any significant energy. And so typically people will provide some form of supplemental energy dissipation that's activated by the rocking to enclose some area in the hysteretic loops. And so we get this characteristic flag-shaped response. And so if we compare that to a more traditional, a more ductile system, which is what we're comparing in this paper, the energy dissipation that you'll see per cycle is quite a bit less. But we get the advantage of having this self-centering, whereas a more ductile system, if you unload from the peak drift, you're going to have a locked-in residual drift, which we associate with needs to demolish the structures. As an example of this, I thought I'd show a video. This video is getting old at this point. This goes back to my PhD almost 15 years ago now. But this is shake table testing that was done. Displaying here. So in the middle, you see the overall view of the 8-story frame that we tested at 30% scale, close-ups of the two corners. So you see it lifting up from the foundation. For the test that we ran here, we used friction-based energy dissipation. You wouldn't have to do that in practice. Anything that'll dissipate energy should do the job. But this rocking response is softening things, but in a way that's not associated with damage. And so we can get the advantages of the nonlinear response without needing to have the structural damage that is typically associated with it. These have been built. So in California, a couple of examples, Orinda City Hall, just kind of east-ish of San Francisco, designed by Tipping Marr. This uses a rocking system. The Packard Foundation as well uses controlled rocking. In New Zealand, there are a number of examples as well. Two of them that I picked for this slide are Te Puni Village in Wellington and 141 Cambridge Terrace in Christchurch. Built after, Te Puni was before the Christchurch earthquakes, but not significantly affected by them. Not affected, really. 141 Cambridge Terrace was built afterwards. So the question of how did it do during the earthquake is not something that we really know the answer to yet. But they have been built. They're not codified, and so they're not common. Now, one of the things that people often wonder about is this impact that you have as the system is lifting up and then it feels like crashing back down. And as far as we can see, both like from the video that I showed you, we went looking to see the impact of that, forgive the pun, the impact of impact in that case. But it wasn't anything really significant. You can see very large accelerations right at the point of contact, but those had dissipated by the time you reach the floor masses. Where we do start seeing some accelerations is more actually influenced by the higher mode effects, that just like a reinforced concrete shear wall, when you form this moment hinge at the base, that doesn't fully cut off the higher modes. So this was some work done by another student a few years ago, looking at the floor spectra for controlled rocking braced frames. And what we see in this case is the peak accelerations were maybe a bit higher. And then we have these large, that laser pointer back on, we can have these large spectral peaks in an analytical model. How much that translates to a real system, I think, is very debatable, but we start seeing it in the model. And so the question that this raised for us was, okay, we're avoiding structural damage by having a rocking system, but often our seismic losses may be heavily influenced by the damage to acceleration-sensitive non-structural components. And so do we need to worry that we are sacrificing them in order to get the structural benefits that we want? And if so, how does it play out overall? Is this a net benefit? And so that's really what was driving the work that's presented in the paper I'm presenting today. So coming back to this question of whether it's worth investing, I'll now switch gears a little bit into the methodology that was used in the paper that's published in Spectra. 4 structural systems that we looked at. So we took one floor plan of a structure. We took it at 3 stories, 6 stories, and 12 stories for a site in Los Angeles with the parameters given there. And then we looked at 4 different seismic force resisting systems. One of them was a steel moment frame. One was a concentrically braced frame. One was a buckling restrained braced frame. All 3 of those designed according to ASC 7 using the current provisions. And then the 4th one is the controlled rocking braced frame. It's not codified, so we followed some design guidance that I had developed a number of years ago. You still need to assume an R value, so it's nothing crazy to design. You're still following an equivalent lateral force procedure like you would for most systems, and we assumed an R value of 8. I think you could push to larger values of R, but we held it at 8 for the study. Modeling, I'm not going to have time to go into detail because there were 4 different structural systems that all needed to be modeled. But just to highlight that it was all done in OpenSeas, using reasonably advanced models that are trying to capture all the way to the level of collapse. So we've modeled things like fracture of braces, deterioration of beam column hinges, panel zone action, all of these things included in the models, and those are validated, but I won't be able to go into much detail on them today. In terms of estimating repair costs, we follow the P58 methodology. The numbers available there are $2013, so these numbers are probably pretty low by today's standards, but $250 a square foot for the moment frames, $175 for the 2 different kinds of braced frames. And then there's a question of what do you assume as a construction cost for controlled rocking? We assumed 2% more than the BRBF, which might be lower than you might expect, but honestly, from talking with the people who have designed the ones that have actually gone up, it's very hard to do a cost comparison without an actual project, but generally they're talking a couple of percent maybe, and in some cases even cost neutral to be able to use a controlled rocking system. This is not an astronomical cost increase, and so we thought 2% would be, if anything, probably on the high side of what the construction cost would be. In terms of evaluating damage along the way, the fragility functions are mostly taken directly from the updated P58 database with a couple of further modifications. Demolition conditioned on residual drifts is an important consideration. We took a median residual drift for this study of 1.5%. That's higher than the default impact. It follows another reference, largely because we didn't want to overly penalize the systems that we're comparing rocking to. So this is probably actually less favorable for rocking than a different assumption that you could make. For estimating damage to controlled rocking braced frames and how you would quantify that, the fragility functions there generally are following a concentrically braced frame, accounting for the different, a story drift is more coming from rigid body motion for a controlled rocking system than for a conventional braced frame. So that's captured in the model. And then the computations, most of them were done using Pelican, out of the NEARI Sim Center. So that was our main computational engine for the work. For the loss assessment work, the actual analysis was all done in OpenSeas. So then looking at the results, looking first at the structural performance, we see an influence of the different structural systems. For this particular case, the time traces actually line up pretty closely for this particular earthquake. That's not always the case. They have different periods from each other. But a couple of things that are fairly typical that I wanted to highlight. One is for the controlled rocking system, often what we see is the peak is very similar to the other systems, but you might have a peak in the opposite direction that's still not the peak overall, but is larger than for the other systems. So that tends to be, when you think about having less energy dissipation with a controlled rocking system, you might worry about that less reduced energy dissipation. Typically, though, what it means is just you actually have a more symmetric hysteresis during the ground motion. And so the damage associated with that is probably not particularly more. The piece that I'll also point out is the residuals here. You see for the braced frames, we have not huge, but between 0.5 and 1% residual. This is a design level earthquake, and 0 residual from the rocking system. If we look at average response overall, so what's plotted here is the 3-story structures, the 6-story, and the 12-story. The first set of plots is the peak story drift ratios. We see the moment frames are typically having the largest drifts. The smallest are typically the concentrically braced frame. And then the CRBF, although it's quite stiff, once it rocks, it softens pretty significantly. And so it's somewhere in between. Peak floor accelerations, it surprised me a bit, actually, that the moment frames were reaching the largest accelerations overall. That was generally because they were drift limited in design, which meant that the forces were not capped in the same way for the moment frames as they were for some of the other systems, and force is mass times acceleration. So if the force wasn't capped, the acceleration wasn't either. The residuals were essentially 0 for the controlled rocking system, and not huge at the design earthquake level, but still noticeably larger. And if we look at the collapse fragility curves, the vertical line here is showing the MCE. We're generally less than 10% probability of collapse. That's what you would expect and hope for. And then the collapse margin ratio is what you would expect. So then looking at intensity-based losses for these systems, what's shown in the top is half of the design earthquake, and then the MCE. And for most of these cases, what you see is the moment frame has the largest losses at that intensity, then the concentrically braced frame, then the BRBF, and then the CRBF is the least. And if I look at, say, the MCE level, you'll see that the controlled rocking system has essentially no demolition losses, essentially no collapse losses. None of them really have very significant collapse losses, but the demolition losses are quite significant. So the probability that you have residuals that are large enough that you need to demolish the building are quite a bit larger for these systems, as you would expect. Also, kind of as expected, the acceleration sensitive non-structural component losses, typically a bit more for the controlled rocking system at all intensities, but that cost is more than outweighed by the savings in demolition costs for the case where you have large residual drifts. And then if we integrate that through the hazard curve to look at time-based losses, so what's shown on the y-axis here is the expected annual loss, we see the same trend where we have the least for the controlled rocking braced frame. None of these numbers are all that large, but it's lowest for the controlled rocking system, where some increase in acceleration sensitive non-structural component loss is more than outweighed by the savings in demolition and to a lesser extent collapse losses. Then we also looked at kind of a cost effectiveness ratio. So what these are showing on let's start with the y-axis, is an assumed increment of cost relative to a concentrically braced frame. On the x-axis is a return rate. So, inflation typically 2 or 3%, looking a bit more than that. And then the contours here are different numbers of how much are you saving in like net present value over the lifetime of the structure with this system, either a controlled rocking system or a BRBF, relative to a concentrically braced frame. And what we see is that it's populated, that in general, there are some savings. These are not huge savings. Like you'll probably make more money there are other higher risk endeavors that you could take to make more money, but it's coming out positive. It's not over the lifetime of the structure. This is a net win. So revisiting then this question of, is it worth investing more in a more resilient steel seismic force resisting system? Before capping that one off, I do want to highlight things that we didn't consider because there were lots of them. We looked at one building location and archetype, 3 different heights, but one floor plan. We didn't look at modeling the gravity framing, which tends to reduce the residual drifts that you have. It's in there for P delta effects, but not for the effects on the lateral resistance. We had one damping model that we had to assume. We have one set of ground motions that are probably a little bit on the high side relative to a conditional spectrum. The fragility curves are all baked into FEMA P58. Those are questionable. The residual drift thresholds, again, that's an assumption. So there's lots and lots of pieces, consequence functions as well. And one time horizons, we assumed 50 years. And then one that I really wanted to highlight is indirect losses. All of this is based on the direct cost of repairs as estimated according to FEMA P58. But often it's the time that you're out of the structure that is more important than the repair cost. And so that's something that's not included in this study. But with all of those caveats there, is it worth investing in a more resilient steel seismic force resisting system? My one-word answer would be yes. I think that the controlled rocking systems can be cost effective in the long term. And we didn't know that going into this. We honestly were not sure whether the whether potential increases in acceleration-sensitive non-structural component losses would outweigh the benefits. And it seemed that things were looking good for resilient systems here. But I do want to highlight how the irreparable losses is what we called demolition, collapse. Those are things that you can't fix non-structural if you have to demolish your structure. And those can be very significant for the ductile systems, even if it's in a very large earthquake. Over the lifetime of the structure, that can be significant. And so then coming back to this image from before, I think it's important that we're thinking about things not just in terms of structural, not just really even in terms of non-structural, but in terms of a community. There are lots of buildings that go into that. And so I think it's important for us to move towards reducing those losses there. Just before wrapping up, one last thing that I wanted to highlight. If you were interested in this paper, I'd like to highlight a couple of other papers written by same authors with Amir and myself. One was we took a similar methodology and we looked at, there's lots of dials that you can turn on the design of a controlled rocking system. So looking at how you would do that to optimize to reduce the losses, that's one. There's another paper here on looking at our fragility curves for non-structural components that are acceleration sensitive are all based on the peak floor acceleration. But as a structural engineer, I use the peak ground acceleration for almost nothing. Usually I am using a spectral acceleration. And so applying that thought process to look at our fragility curves is a paper that we published as well in EESD. And then finally, getting into the weeds on consequence models in like FEMA P58 and economies of scale there. So I will put those in the chat after I wrap up here. I'll acknowledge financial support from our federal and provincial funding bodies, and I will stop there, hand over to the other speaker, and I would love to answer some questions after both presentations. Thanks so much.
Thanks, Lydell. Awesome job there. And thank you for sticking to the time. Really appreciate it very much. So our next speaker is Professor Chukwuebuka Nweke. He's a professor of civil and environmental engineering at University of Southern California, Wiebe School of Engineering. He directs the research NEST research group, where his research really focuses on solving problems at the intersection of geotechnical engineering and earthquake engineering, seismology, and geomorphology. So really a broad spectrum of work Buka does, and it's a pleasure to introduce him. He completed his bachelor's at UC Davis, master's and PhD at Berkeley, worked as a postdoc with Professor John Stewart, I guess, at UCLA. So really a wide range of topics, and I'm so glad to introduce him. And today he's going to talk about Southern California basin and non-basin classification algorithms for ground motion site amplification model applications. And he co-authored that paper with, I believe, his student Rashid Shams. So take it away.
Can everybody hear me? I'm assuming everybody can hear me. Is it good to go? Perfect. Good afternoon, everybody. Welcome and thank you for joining us today. Over the next 20 minutes, I'm going to pose about 5 major questions that will kind of highlight and divulge the motivation, justification, objective, and impact, and the approach of the content associated with this paper that was published on Earthquake Spectra. To clarify, we are speaking about sedimentary basin classification model for semi-empirical site response modeling and assessment applications. So let's jump into it. And I'd like to thank the hosts and Kishor for a wonderful introduction. So we'll jump right into it. So, oops, let me fix this. So the first question you asked, which is a fundamental question to ask regarding this paper, is why is distinguishing between basins and non-basin critical for accurate seismic hazard assessment? Well, in this case, these 2 videos here should provide some understanding of why discerning between basins and non-basins sites is important. On the top right, you're going to see the displacement history of 2 GPS sensors, one in a non-basin environment, which would be a purple circle, and the other in a basin environment, which would be a gold circle. On the bottom left, what you're looking at is a live footage, live recorded footage of the response in the basin environment. So let's take a look at what's going on. Oops. So what you'll see here is, in the beginning, this is for the 2015 Kathmandu Gorkha earthquake in Nepal, and you'll see the purple circle is going to go, and it's going to keep shaking, and then the gold circle, which is in the basement, will go, and you're going to see drastically different behaviors in amplitudes between both of them, for the basin and non-basin, for the same earthquake. And you'll see in the video in the bottom left, what that looks like in real life and how that can be quite disorienting. And also, in this case, for this video, there wasn't any damage in this location, but not too far away, there was a lot of damage and people lost their lives. But this is just showing you the differences between what's going on for the same earthquake between two different site conditions. And some of you will ask, okay, what's the cause for these differences? Well, in a simple way, the cause for these differences essentially is site response, right? So here in this video, we're showing kind of the impacts of site response relative to building performance and ground conditions for the same earthquake event, right? So you see 4 identical buildings founded on 4 different site conditions: bedrock, consolidated sediment, sand and mud, and in this case, supersaturated sand and mud. And what you see is that the P and the S waves and the surface waves, as they essentially pass, will manifest as different amplitudes and intensity depending on site conditions. So much so that the impacts of the buildings will be different. In this case, the S and the surface waves, the S waves and the surface waves, which are pretty critical for engineering design, will lead to drastically different building responses and building damages as you go from competent to less competent site conditions, as you guys can see right here. So I guess you can, from this level, as you're seeing these differences in the example of what's going on, the next question you will ask is kind of, what is site response? Well, in this case, site response is, the way I've defined site response is the alteration of seismic energy due to variations in the properties of the subsurface geologic materials, so sediments and rocks that we've seen. These things can be influenced by a variety of physical mechanisms, and this includes impedance and damping effects. We're going from a stiffer material to a softer material, can lead to pretty much increases in amplitude. Resonance effects, where if your structure or your system has matching energy with regards to matching frequency content to the energy of the seismic wave, you might have the coherency and further amplification. You also have topographic effects that are included in site response, which essentially just showing you that the shapes and the orientation of certain things can lead to focusing and trapping and dispersion and further constructive coherence or destructive coherence. And then you have the last one, which we call geometric effects, basin effects, which essentially is saying that we have 3D effects that can essentially create a little bit more craziness as we go along. In actuality, these 3 effects are actually buried within the basin effects, because the impedance and damping effects going from bedrock to basin, and within basin is going to change. The resonance of each basin is going to be different, and the shape of the basin will act as topographic effects. So these things are all embedded within site response. So the next question you would ask is, how do we currently model site response in sedimentary basins, and what's kind of the key limitation, right? So here I'm going to show you an example of what I call basin effects mechanism, site amplification physics. And this is going to show how we, in ground motion modeling, we essentially partition the contributions to these things into bins, as engineers love to do. The first thing we do is we have a source component. And the source component is a function of magnitude, which is telling you how much energy, and the faulting, which tells you what kind of thing produced the energy. The next thing is the path, which tells you what's going on between the source of your energy and close to your site. Once you get to the site, you have essentially contributions from the basin and the deeper portion of the basin, shallow portion of the basin, that can be focusing and resonance and the likes. So this is what we do in quantifying what's going on with an earthquake at a site. Another situation you can have is you can have the earthquake traveling long distance and entering the basin, and you can still have your resonance, but you could also have reflections that can bounce back and forth that can lead to generation of propagating shear waves. And these propagating shear waves will further increase your ground motion intensity and add to the whole amount of prediction or the estimation. So the question now is, how do we do this specifically for basin effects in ground motion models? Well, in ground motion models, the way we do stuff, we look at the site effects. We use some measurement of the subsurface condition, which in this case, we use shear wave velocity measurements. And from these shear wave velocity measurements, we parameterize this into the VS30, which is the time average shear wave velocity in the upper 30 meters, and a basin depth, which is the depth to a particular surface horizon, or shear wave velocity, like 1,000 meters per second. And what these two tell you, essentially, to give you a representation of kind of the stiffness and strength of your site and the amount of material on your site that's relatively going to be affected by these amplifications. And the VS30 itself gives you a first order scaling of this as a function of period, while the basin depth gives you a second order version of this amplification relative to that VS30 amplification. So it tells you if you have more material, less material, how are we going to amplify? So in order to do this in a quantitative fashion, you realize that these two parameters are captured from the same measurement, so in some cases they're correlated. So in order to isolate that, we have to essentially establish a relationship between the VS30 and the basin depth, and use that relationship relative to our data to create a differential. And this differential is what we use to essentially relate to site response on amplification, such that if you have a positive differential, you're going to amplify relative to the VS30 case. And if you have a negative differential, you're going to de-amplify relative to the VS30 case. So that's kind of how we capture these basin effects. If you notice, though, throughout this whole thing, I have not mentioned if you're in a basin or not in a basin. So this approach assumes this is consistent for all sites, which now we know is not necessarily the case, right? So if being in the basin, you're going to have different behaviors than if you're not in the basin. And in order to, you have to be able to separate the two to be able to understand what's going on. So we did just that. We went through with a panel of experts, and we went through every ground motion station in Southern California and assigned them as basins or non-basins. So the red circles and the purple triangles. And in addition to that, we also assigned intermediate sites, which is the basin edges, so close to the margin, or valley sites that we call smaller basins, which essentially are smaller sedimentary structures. And we did this in an iterative fashion with experts to essentially establish this. And we saw fruitful things in our paper that's also published in Earthquake Spectra for site response in basins in 2022. And what we did here, some will say, and which is true, it's somewhat subjective. So different analysts may have different views on what is a basin or basin edge versus non-basin or valley versus basin. So our goal for this paper was to kind of develop a quantitative means to be able to repeat this classification system such that it is not subjective in any way. And the question now we have to ask is, what can we use as an indicator that can replicate what we did as from a visual standpoint? And we went through a suite of parameters and came into the conclusion that surface texture was the best way. But overall, this is kind of the criteria that we use to identify bases. So it has to be within a large flat region. Edge has to be within some margin distance of the edge. Valley is a smaller version, and Mount Hill is pretty much has high topography. So the goal was, why was surface texture selected as a primary feature? Because I believe surface texture was what did the best job of replicating what we saw as analysts in our eyes. So that's the question that we wanted to ask. Why was surface texture selected as the primary feature for basin classification? Well, in order to do this, we have to essentially go to a suite of features. So we started off looking at elevation. And we use elevation because when you look at elevation, this is a digital elevation model of Southern California. And you'll see, if you remember those boundaries for the basins, that the basin locations are typically low-lying relative to the other non-basin features. But if you look closely over here, you'll notice, I don't know if you see my arrow, you'll notice that the LA basin, which is relatively deep relative to the San Fernando basin, has slightly higher values because the color is slightly brighter, right? So, and you can look at the Mojave Desert as a relative basin as well and see that's also high elevation. So this is kind of indicating that elevation may not be the best classifier for basin, non-basin conditions. And this can be proven when we go to Grand Canyon. We have the same flat, low-lying areas that we would consider basins, but this is not a basin. These are sedimentary rocks that are outcropped. So, and again, this is just showing that elevation it's not going to be a good indicator or classifier of basin, non-basin. So we went forward and we said, let's look at the ground slope. So we essentially established the ground slope for the region. And what we see here is that on average, the slopes that are low are within basins, the slopes that are high are outside of basins. But if you notice, within these basins, in these areas, you see there are some regions within the basins that have high slope values, right? And there are also some regions within the non-basin regions that have low slope values. So again, though it does a better job, it's still going to have that suffering of confusion and nuances between basin and non-basin classification. So we decided to see, okay, the slopes may not work as well, so let's look at curvature. And we found that curvature worse than slope could not do a good job because we look at curvature, this is general curvature, the blue and the yellow and the reds show either really positive or negative high curvature values, so convex or concave, versus the pink, and what you see there is pretty much no curvature. And what you see, that pink is prevalent everywhere. So you can't use curvature to discern between basin and non-basin. It's not going to work really well. So we chose surface texture. And what do we mean by surface texture? So we define surface texture as a standard deviation of the ground slope over a given radius. So here we have a radius that we move, a moving window that we move, and we calculate at the center of that point the standard deviation of all the stuff within that moving window. And that radius of that thing could be bigger or smaller depending on what kind of resolution you want for your surface texture to be in. And what this is doing essentially, this is essentially saying that if you were, let's say you're within the basin, the standard deviation at the center of the basin should be low, so your surface texture should be low. Versus as you get closer and closer to the edge, and you start to pick up these non-basin features, your standard deviation of the slope will go up, so your surface texture will go up. And if you go to a non-basin location, you should have high surface texture because you have high standard deviation of slopes, right? So this is essentially trying to capture essentially a smoother representation of slope such that we can essentially use that as a classifier. And it does a good job, and we found that it does a good job. And we show this, in order to show this quantitatively, we have to sample the entire region, at different sites, and at all these different sampled sites, we captured the elevation, slope, and curvature and the surface texture, and then we compared them. And the comparison here, what you see here is a histogram of these values throughout the area. And you look at for green is the ambiguous zone, so these are zones that are not basin and non-basin, but we have the basin and the non-basin location. If you look at elevation, there's a significant overlap between basin and non-basins. So you can tell already that it's not a good classifier for basin and non-basin, just looking at that. Same thing with slope. Slope has a little bit of an overlap between the two, and general curvature has a significant amount of overlap. We look at surface texture, in this case, we're looking at about a mile radius. It has the best as far as separation between basin and non-basin. So we decided to go with that. Now, I mentioned that the radius can vary from different sizes. So we actually did a PCA analysis that included surface texture of different radiuses, and we found that 1.6 kilometer to about 2.5 kilometer works best. So we stuck with those two as they both captured most of the variance in the data. So now that we have this, the next question is, okay, now that you have the feature that you want to use, now the question is what algorithm can provide the most effective and practical classification model? Because again, we want this to be practical such that we can be able to, people can use it in a robust manner. And how was this determined for it to be chosen? So as far as the machine learning algorithms are considered, we chose a suite of algorithms such as logistic regression, which essentially is a binomial classifier that uses likelihood to determine the chances of being in one group or the other. We use the k-nearest neighbor, which is a distance-based classifier that's hinged on clustering. SVM we use as a separation-based classifier that kind of partitions data into effective groups. Decision tree is a classifier that essentially operates on a hierarchical cascading criteria assessments. And random forest is a kind of a collection of decision trees that's aggregated and averaged, kind of like a weighted average. Naive Bayes is another likelihood classifier that's based on observed features, but assumes that features are independent, conditionally independent. And then we have bagging and boosting. So bagging is kind of an enhancer that uses bootstrapping, random sampling, and boosting essentially is a sequential training enhancer that we use to essentially reduce the bias in our model. So we used all these models, these algorithms to try and develop a classification model. And the metrics we used to kind of assess these were recall, precision, F-score, receiver operating characteristics, and area under the curve. So these are typical things that people use in the machine learning data science space. And what you want here in this, as far as the recall, precision, and F-score are concerned, those combined can give you a good understanding of what's going on. But the ROC and AUC do a kind of a better job at giving you a direct representation of what's going on. And in this case, the ROC curve that you see here, the goal you want is that you want for every true positive rate, you want pretty much a zero positive rate. That would be the best case scenario. So in that case, you have in that situation, you have an AUC of 1. A poor performance would be for a given true positive, you have an equal false positive, and that would be the 1-to-1 line. So what we saw here is that logistic regression, SVM, decision tree, and naive Bayes provide the best kind of performance according to the AUC and the ROC curves. And we chose logistic regression because naive Bayes has that unrealistic assumption of things being conditionally independent. And we chose logistic regression because it provided the probability of being in the basin and had a functional form that was readily available and easy to digest and is palatable for people to use. So that's what we chose and we went with. And the outcome of that is that you see here is a spatial map that shows the probability of being in the basin as far as the color grading, where lighter colors, yellow is 100% chance of being in the basin, high chance of being in the basin. Darker colors are essentially very little chance of being in the basin or high chance of being in a non-basin. And when we compare it to the expert data that we had earlier, we have the red circles as basins and purple triangles as non-basin, you see that essentially these things overlap relatively well. So this is saying that the model is doing a good job, right? And again, remember, this model was developed on data that not on this data, but data that was queried on basin and non-basin. So we've seen that we're doing a decent job. Now, the next question you might want to ask as our last question is, how might this basin classification model be implemented in future seismic hazard assessments? And what are its limitations? So the first place that this will probably provide significant value for is the National Seismic Hazard Model from the USGS. And this is important because in developing these models, they use these semi-empirical models and simulations and a few other things to develop their representation or their estimates of intensities for given earthquake scenarios. And knowing that you're in the basin, non-basin, as you saw earlier, is important because that would tell you how things are going to amplify. So this classification model can help in guiding this the estimates for these analysis. And once you're able to do that, you're able to provide better representations of the probability of shaking and hazard going forward. So in this case, what are the limitations and future endeavors? Well, the major limitations is that this classification model is hinged on surface texture. Surface texture is a geomorphological based feature that is hinged on the ground surface. So anywhere that has basins that do not adhere to the same conditions as Southern California, i.e. glaciated regions where a glacier has carved the surface, and even though it's a basin, you have significant topography, the classification algorithm is not going to perform well in that region. It also has some places such as areas with cemented plies might also pose a little bit of issue, but that's a little less of a problem because you can use judgment to essentially address that. Now, future efforts, I guess the simplest future effort is that we're going to try and resolve this glaciation limitation, and also try to employ other geologic informations such as surface geology units and a few other things to try and help in this effort. The next thing that we would like to do is to essentially investigate the effects of length scale impacts, or what feature length scales are looking like, and cause associations, whether it's correlation or causation, as well as trying to regionalize the model to see if it can perform better. So those are our hopes and our dreams that we're going to be working on to try and improve what we've done so far. Now, I want to ask, what can I clarify, elaborate on, and further explain? And I would like to take the chance to thank the people who have helped me throughout this process, from my postdoc to now. My student Rashid Shams is what helped me out with this work quite a bit, and I believe he's online as well. So I appreciate you guys, and thank you guys for taking the time to listen.
Thank you so much, Buka. It's a great job, and thanks for, again, respecting the time. We have a few questions already there. I encourage everyone to please type in your question. Just remember that this webinar is recorded, and it will be provided on the YouTube. So your questions are very important, and hopefully whoever is listening to those YouTube videos, they could actually see and benefit from those questions. So I really encourage you to type in your questions so our speakers can answer them. Yeah, so we have first question from Can Yang. Forgive me if I'm pronouncing your name incorrectly. Great question. Thanks, Lydell, for sharing this important research. I was wondering if you might have any insights into the damage thresholds that were used to determine whether buildings require demolition or reconstruction following the Christchurch earthquake sequence or any other big earthquakes. So, Lydell?
Yeah. For Christchurch as an example, I think we could talk about this for hours. I think it's a fascinating question, but a couple of points that I'll emphasize. One of them is the residuals in most cases in Christchurch were not actually all that big. And even with small residuals, there were still a lot of demolitions. And there are many factors for that. One that I think sometimes is not talked about as much as it probably should be is insurance. My understanding of the insurance landscape in New Zealand was that many of those buildings had a provision in there that they were entitled to something that was essentially good as new. And once you've yielded a rebar that's embedded in a piece of concrete, it's pretty hard to get it to be as good as new, even if it might be okay. So my guess is that if there was exactly the same level of damage in someplace on the west coast of North America, where insurance penetration is much less, that there would be a lot more creative problem solving to find ways to make things work. So I think that's one of the factors in there, but I think it's still overall, I think still this thrust of how can we get structures returned to service more quickly is an important one. Exactly what it looks like will depend on a regional context.
Great, thank you so much. I guess we have another question for you already. Tom Hill, he's asking, for the controlled rocking brace frames, what is your recommendation for the damper type to damp out the high axial overturning compression at the base at the end column? So good question. That's great.
Yeah. This is one where actually the intuition is usually a little bit off on this. Mine was too. So it feels like the big force is going to be when the system comes back down. It's not, because it's zero immediately before. So at the moment of impact, there's zero force right there. And it starts developing over time. It's just like, it feels like when a plane lands that the big impact force is going to be when it lands, but actually it's when it's sitting with a full tank of fuel at the end of the runway about to take off. So that impact force is not as big as you might expect. But still, the question of what kind of energy dissipation would you want to use is an important one, but I think it depends on the economics and just the practicality of where you are. You can use pretty much anything that will in some way be activated by the rocking in order to dissipate some energy.
That's great. I guess I have one question since maybe people are still typing. So Lydell, I was curious, like there are coupled and decoupled systems within the controlled rocking systems, right? So I was curious, like why this system is still not getting as popular as it should be, as your results clearly show that in terms of non-structural damage and cost, really it's just a great system to really control that economic impact at the end of a large earthquake, right? So I'm curious, like what are the practical challenges associated with either designing or constructing such systems? Of course, it's not codified yet, so people always have that kind of a anxiety.
Yeah, there's always a hesitation with that lay.
Yeah.
I think it's also a big question. I think the lack of codification is a piece of it. So if I think of other like high performance systems, you don't see a lot of structures with viscous dampers, even though I think viscous dampers can work really well. You do see base isolation, not as much as I think there probably should be, but there's some. And there's some provisions in the code, but it's not as easy as other systems. And so I think there's that practicality aspect of things. And I think a piece of it is just people are intimidated. Like, especially when it's not in the code. I think the real potential for a rocking system is for some of the just like regular buildings, not something fancy, not where it's a high importance structure that you're trying to base isolate it, but just doing something simple. But I think people, without having anything in the code, I think it's people are hesitant to take the step of trying to figure out how to do that. So it's something that we're working on now, trying to move towards that. But that's my feeling.
That's great. Thank you so much. And I think we have another question for Buka. If you can come on the screen. We have Nushin Hadidian. Sorry for my pronunciation. Thanks for the nice presentation. Can define several types of basins based on the geometry, material, heterogeneity. I guess she's probably looking for some examples or different types, the definitions, and what are the differences can affect on damage classification. Luca, you want to take a stab?
Can you hear me? I was reading the question, so I'm trying to understand essentially what they're asking. I'm gonna try and repeat, maybe rephrase what they're asking. I think maybe they're asking about if you have different types of basins and how that manifests in the impacts to ground motion and how that damages building. I would say this is a very good question because the size of the basin is only one component of a very complex situation, a very complex system, right? So the manifestation of shaking at a site is going to depend on a number of things, including what's going on at the source, and then what's going on between the path, and then what happens at the location of interest. And then there's these things are not independent, right? So wherever the earthquake happens to where your site is, even if your site is consistent, if the earthquake happens in another location, the response to that same building, that same site will be different. And this depends on one, how tall the building is, how much material is beneath the building, what's going on in those cases. So those things do matter. So if you're able to characterize your basin in that sense, you're going to have a better understanding of what's going to happen there, even though there's still more information that needs to be addressed, right? There are within basin features and other things that happen. But that will help you understand more of the damage going to your structure.
Great. Thanks for that insight, Buka. I think another curious question for you looks like, how do you input the data into the system for machine learning?
So again, another thing, I'm gonna try and reframe the question to see if I understand what's going on. And if I'm wrong, please re-ask your question. I think I don't know if you're asking how do you implement the machine learning model that we developed, the classification model, or how did we develop it? So I'll answer both, right? In order to develop the model, what we did was we queried this information, and we essentially, in order to develop the machine learning model, we used the surface texture as queried at all those sites within the Jupyter Python framework to essentially run our analysis, and also our framework to run our analysis to make sure that we're having some epistemic consistency in modeling types. So that's just a regular way of machine learning model development. Now, in order for you to use the model, the best way for you to use the model, what you would do is, for your site, because our motivation for developing this model was to use features that are readily available, right? You don't need to go and do any measurements outside or whatever the case may be. So you can just go get a digital elevation model for your region. And once you have that, you can essentially use geospatial analysis to compute the slope. And then from there, you can use geospatial statistical analysis to compute the surface texture based on the radius that you want. And then you can then input that into the functional form based on the coefficients that you want to use. And then you can essentially calculate that spatially. So ArcGIS, QGIS, they have readily available tools for you to do this. All you would need is essentially the coefficients in the functional form, and then just to do some geospatial analysis to do that. So that's how you would use the classification model.
That's great. Thanks, Buka. Tom again asking, I guess, Lydell, for the CRBF again, what is the amount of redundancy in the system? For one-story frame, there does not appear to be very much redundancy for this cantilever type system. Do you agree?
So there's different ways you could think about redundancy, most of which I think are the same as for any other system. So if you think of like a reinforced concrete shear wall, how many of them you put in to a building is a measure of the redundancy. Same thing would be true here as well. I think probably what you're getting at is that it feels like it's critically dependent on the post-tensioning, and if the post-tensioning fails, then you've got nothing left. Or if you had a system without post-tensioning, maybe it's dependent on the energy dissipation. And there's two pieces I would say in response to that, both of which are reasons why I'm not sure that I totally agree. One of them is if you had a braced frame, you're critically dependent on the brace. And if the brace fractures, then also you don't have a system. So like normally we do get down to a point where you're critically reliant on something. It's just what that something is here is maybe different. The other piece that I would link to that where I'll leave the door open a little bit. Something we've wondered about is what do you want to do to control at ultimate limit states? So sometimes we've thought about, do you have some sort of a lockup mechanism that if you reach a certain base rotation, you reach the end and then it grabs it, and then it just turns it into a concentrically braced frame like you might otherwise have had. And in that way, actually, you have not less redundancy, but actually more, because you have another system that hasn't really started being deformed. It's just gone through a rigid body rotation that only starts getting activated after you've reached all of this drift. So I agree with that feeling of it feels like it relies on something, but as far as I can tell, when you work it through, it's at least as redundant as any other system.
That's great. Thanks for that insight again. Guess we're almost at the time. I would like to thank again to both speakers. You did a great job. Thank you for sharing all those insights and also sharing the papers. And if possible, please, if you are comfortable sharing your email or the place where the slides can be found, I think Elizabeth might provide that additional information. So with that, I want to thank both the speakers again for doing a fantastic job. And Elizabeth, take it from here.
Thank you, Kishor.
Great.
Thank you, guys.
Thank you very much to both our speakers, and thank you, Kishor, for moderating today. I just want to take a brief moment to let you know there'll be a survey that will pop up after the webinar window closes. You'll also get that in the post-webinar email, so if you can take a moment to fill that up, we appreciate it. You can learn more about EERI at our website, and you can join us at that link. And you can also support the work we do, including our earthquake reconnaissance work, by supporting the LFE endowment. And then finally, I just wanted to say again, the webinar is supported with funding from FEMA, from the LFE Endowment Fund, and by EERI members like yourselves. And to the question about slides and recording, the recording will be posted on our YouTube account within the next week or so. And if you're interested in slides, you can reach out to the presenters or to us if you don't have their contact information, and we'll share it with them. Thank you again. Have a great day, and we look forward to seeing you at our next webinar in April.
Thank you. Good job.